Quantum mechanics is the study of a very strange topic. People have a lot of odd ideas about it. When I say the word quantum mechanics, what's the first thing that comes to your mind? What kind of study do you think we're talking about? Super small, something having to do with time. Anybody else?
Atoms.
Atoms? Anybody else? You watch, I'm going to trip over those feet before this is over.
Yeah.
I promise. You watch for me. Get that one on camera. Yes.
Base particles?
Yes. Maybe the base particles of the world. Yes, in the back?
Uncertainty.
Uncertainty, what we call the Heisenberg uncertainty principle. Absolutely. Big part of quantum mechanics. Yes, sir?
Energy packets.
Energy packets, what we might call quanta of energy. Anything else? Yes, in the back?
Computing.
Quantum computing, a whole new field we'll talk about. We'll talk about that tonight, too. You, sir, in the plaid. Your one? Oh, yes.
Hamiltonians.
Hamiltonians, that's the mathematical formalism we use to describe quantum mechanical objects. Anybody else? Quarks?
Probability.
Probability. Good. These are all excellent. Sounds like you know more about quantum mechanics than I do already. So, this talk might not be as illuminating as you would hope. No, we'll see. But all those are absolutely right. Quantum mechanics deals with the study of things at the very smallest scales. Now, in the beginning, this was the scale of things like electrons or maybe atoms. And then eventually developed things like quanta of light as well. Somebody asked me on the way over here, who discovered quantum mechanics? And as we'll see, one of the problems is it isn't one person. It's whole sets of people over the course of life. Let's say, if you want to start with the discovery that the atom is mostly empty, by Rutherford, maybe in 1895, and you can go all the way through Richard Feynman, who won the Nobel Prize for a formulation of quantum mechanics in the 1950s. So if you want to go that far, we're talking like 60 years of work to try to figure out what this stuff is. And as we'll see in just a second, the reason for this is because the problem is very complex. Quantum mechanics is probably the most counterintuitive thing I've ever seen. I take the physics class, I took relativity, and I took quantum mechanics. And Richard Feynman was a very, very famous physicist, and he said this thing, he said, if you believe you understand quantum mechanics, you probably don't. Because it's so counterintuitive. So to begin with, I'll talk to you a little bit about where quantum mechanics comes from as an idea. Like, how do we even get to this weirdness in the first place? And then we'll extend it. We'll go, okay, here's the conclusions you just can't get away from. You're going to have to deal with it. It's really crazy, but it's true. And then from there, we'll talk about some of the implications for things that we even use today. Like, there are quantum mechanical implications for technologies you use right now and probably don't even know it. Let's begin with the study of what's down at the bottom of the world. Let's say some of you probably just came from high school. When you see pictures of atoms, what do you envision? What does it look like in your textbook in high school chemistry or physics? Somebody who was recently in high school. Anyone? Were you not paying attention that day? Looking at that cute boy or girl? Yes?
It looks like a tiny planet with a tiny moon running around it.
Yeah, this is a very common picture, right? It's a quintessential, what we call the Bohr model, B-O-H-R, not boring, Bohr. It might look something like this. If it's hydrogen, you'll see a proton with an electron like this. And this is what we always see. How many people have seen something like that in your high school books at some point? Okay. Absolutely. This is like the quintessential thing. As you can see, the protons and the electrons are both what? Charged and particles. They're little pieces of stuff, like a bullet. Right? And prior to quantum mechanics, this is how people viewed atoms. They said that electrons are kind of like this little planet that moves around the sun that we would call protons. Right? And then we might have atoms that are different atoms. They could have more protons or more electrons or whatever. But the idea is that things are particles. And so if you start with this fundamental premise, that at the bottom of the world, the stuff we're talking about are particles, keep in mind nobody at this point has ever seen one of these things directly. You can't view them with a microscope. Anybody know why? Yes?
It has to interact with the light particle, which doesn't work very well. It doesn't have color or shape or matter or anything like that.
Yes. The atoms themselves are 10 times smaller than the smallest wavelength of visible light you can ever see. So there's no way to actually see them. You put the light through them, it just looks like a big smear. And so no one can see an atom. It's like it's blocked off from you. Right? And so you can't see an atom. So people start thinking, well, I think it's this stuff. Right? This goes all the way back to the ancient Greeks. Democritus, who came up with the idea that there was something at the bottom of the world that was indivisible, which they use the word atomos for. And so when I look at these particles, I go, what's the property of particles that make particles what they are? Like, how do I know a particle is a particle? I go, one of the things about a particle that's important is that it's localized in space. It's sitting in one spot, right? It's not spread out anywhere. The particle is just sitting there. right? And so that alone was the beginning of what we would call the particle view of how things worked. Credence was given to this idea in 1905. Albert Einstein, in that year, published 3 really big papers. And one of them was on this phenomenon called the photoelectric effect. And so in the photoelectric effect, light beams fall onto some surface of a certain type of material. And electrons will then jump out of the material and travel along the material to some side. This is very common today. It's the basis of solar cells. Your polycrystalline solar panels work based on this principle. At the time, Einstein figured that this was due to the quantization of energy. He said that light only comes in specific bundles. Now, the reason that this is such a big deal is because no one was sure before this. I'll show you the wave picture in just a second. But before this, people kind of thought light was probably a wave. They had since Isaac Newton. I'll show you why in just a second. But in 1905, for the first time, Einstein shows that light can also be a particle, this little chunk of stuff that flies in. You go, well, why would that be? Why do I need a chunk of stuff? Why can't it be a wave? I'm going to give you a thought experiment. It's going to sound kind of strange, but work with me. Imagine a room where there are a bunch of people, let's say they're students who want to get out to go to lunch, and you're stuck up in the balcony around them, and they have a toll booth. And the toll booth only takes quarters. Okay? So if you throw Eric a quarter, Eric can go at the end of the toll booth and click, and put his money in the toll booth, click, and go out and leave. Simple enough. Can I throw Eric 5 nickels to get 5 nickels to get out of the room?
No.
Why not? The toll booth only takes quarters. Didn't I throw Eric 25 cents in the form of the 5 nickels?
Yeah.
Yes, but it doesn't work because it only takes quarters. The money is like energy. Eric is like an electron trying to leave the material. It only works if you throw the right size bundle at once. You have to throw him a quarter. It doesn't count to give him 25 cents as little pennies. He has to have a quarter to put in the toll booth. Okay? And so Einstein proved that energy only came in these specific bundles, like say quarters, for example, instead of nickels, or as a continuous thing. Right? Yeah, you just throw money at him in a continuous little stream, and it would eventually add up to be 25 cents, and he could leave. So it would work. And so the energy of these light particles, which we call photons, the energy gives them what we would classify as their color in the visual wavelengths. So for example, a red little photon of light doesn't have as much energy as a blue photon of light. So for example, if you throw the blue photon onto the material, sure enough, electrons go bloop and leave just fine. You can throw red on it all day long and turn up the intensity so it's really bright red, nothing happens. Doesn't work. This proves conclusively that light behaves like a particle. Simple enough, right? We go, good, we're done. Thanks, that was a great talk. It's been 12 minutes. You go home now. Not quite yet. Because in 1905, Einstein showed this, and that shows conclusively that light behaves like a particle. Everybody thought we're done. Light behaves like a particle. Thanks, that's great. Problem is, we also have experiments that show light behaves like a wave. You go, oh no, it's terrible news. Because that seems to directly contradict what I just said. Particles and waves do distinctly different things that directly contradict one another. Think about this for a minute. If this is a particle, something like this is a wave. And I go, where is the wave? And the wave isn't at just one spot in space. It's spread out. It's like between here and here. Right? And so I go, well, the wave is spread out. Particles are localized to one place. I can point at a spot and go, that's my center. Now, particles have spatial extension, meaning they have size. But I can point at them and go, there's the center of my particle. I can make a wave miles long and spread it out. Right? Anybody who's been surfing knows waves aren't in one spot. They're spread out over some distance. Okay? This is a problem, because that means I now am looking at things that act as though light behaves like a particle, and it also behaves like a wave. And those two things are fundamentally incompatible with one another, at least in the early 20th century we thought they were. How that would work out is what we're talking about. And so the idea is that since these things diffract and interfere, I can show you, this is what they would look like on a pattern. This is a very common experiment called a single slit experiment. Take a beam of light coming through, we put a little tiny slit right here, and we let the light go through. And as it does, it starts to go whoop, 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 and spread out. Okay? As it does so then, it's going to hit onto a screen, but the light waves will interfere with themselves, giving you this pattern on the screen called an interference pattern. These green bands. This green line is showing you the intensity as you go down the strip. So it's kind of intense, more intense, really, really intense, what we call a central maximum. Then a little less intense. Black spots are where it's underneath, so it's a negative number. So it looks like things way get down. Okay. And so the point is, this is not what you would see if you threw particles through the slit. To give you an analogy, I'll show you like a 2-minute video here in just a second. If you threw waves through, imagine throwing ocean waves through like a little barrier, like say in a jetty, you'd expect them to smear out and make a pattern like that on the seawall. Imagine instead taking, you ever been to a carnival? There were these things they had before Xboxes, they were called carnivals. And kids would go there and do fun games and get their money taken away. And so they used to have this game. Have you ever seen this game? This game where they had a machine gun that had bees in it. And you'd have to try to shoot out the star or whatever. If you shot out all the star, you won a prize. You guys know what I'm talking about? You're like, I'm crazy. No one's ever good enough for it. It's ridiculous. Nobody ever wins the big bear. That's how it goes. Shooting the particles is like shooting the BB gun. So imagine you shot the BB gun at a single slit. You'd expect like a pile on the backside, instead of some pattern like that where you get some here and some there and some here and some there. And so the problem is, these two results seem to contradict one another. There's this very fundamental problem. In the early 20th century, people don't know what to do about it. You know, which is it? Particles are always found in one place and hit like bullets. Waves spread out in space and interfere with each other. You know, which is it? It literally depends upon which kind of experiment you run as to which conclusion you get. Think about this very carefully. This is the problem. You know, this means if I run the experiment one way, they act like they're waves. I run the experiment a different way, they act like they're particles. This is problematic. There was that old expression, I can't remember who it was that coined it, it might have been Schrodinger, who said, light is a particle Monday, Wednesday, Friday, a wave on Tuesday, Thursday, and Saturday, and takes the day off on Sunday. Because nobody knew. For like 30 years, everybody's going, how can you possibly, they did experiment after experiment, they tried to use better detectors, nothing works. You know, and so this fundamental incongruity, the idea that lies with a particle and a wave, is where we get to at around the year 1920. And in that year, it becomes, we've got a problem. Nobody can figure out yet how to fix it, because it seems like they're getting conclusions that don't make much sense. And nobody can explain things better than, of course, Morgan Freeman. So let's listen to the words of the maestro himself.
Quantum theory works, even though it shouldn't. And perhaps the ultimate proof of just how unsettling quantum mechanics can be is something called the double-slit experiment. It will make you question whether reality exists at all. This simple configuration shoots particles of light called photons, one at a time, through two tiny slits in a screen.
We have a laser which produces light. This light is attenuated such that only one photon at a time emerges. This photon passes through a two-slit assembly, and then we have a camera which registers the pattern behind the two-slit assembly. So what we see is that the photons arrive one by one on the screen, some here, some there, and it looks pretty random.
Since the photons travel one by one, some through this slit, some through that slit, you would expect them to leave a pattern of two stripes on the wall. And you would be wrong. They mysteriously create a band of stripes. This is what you would expect to see if a constant beam of light shined through the two slits. It would spread across the wall like a wave. So how can single bullet-like particles of light create a wave pattern? This could only happen if the particles go through both slits at the same time. In other words, the particle is in two places at once. But strangest of all is what happens when you put detectors next to the slits. When the photons are being watched, the wave pattern disappears. Take away the detectors, and the wave pattern comes back. This suggests that we can change the way reality behaves just by looking at it. Does this mean that reality itself is not real?
The modern answer is that the path taken by the photon is not an element of reality. We are not allowed to talk about the photon passing through this or this slit. Neither are we allowed to say that the photons pass through both slits. All this kind of language is not applicable.
This is I think, the fundamental concept to grasp in quantum mechanics. The idea, if you get this, you really got it. And so let's review it just very quickly one more time. The idea is that there are two slits, and you're shooting photons through. And you're going, well, are these photons a particle or a wave? Einstein says they're a particle. People since Isaac Newton said they're a wave, because we see interference. And so if you shoot a bunch of them all at once, they end up making a pattern that looks something like this. If you have a bunch of light, this is taken from the view, from the top view, there are two slits like this. It's a little tough to see. Turn my lights for just 1 second. And so imagine you have light beams like a source like this. If it helps, imagine this being, these are the tops of waterways. And so you have like a wall here, like a seawall with 2 holes in it. Okay? And so when these guys go through, you expect the light to do something like this, or the tops of the waves. Either way, same thing. And so they'll go through and do something like this and interfere with each other. So some of the high points of the wave will hit some of the low points of the wave right next to it. Does that make sense? Okay. And so some of the points, when they hit this wall, will cancel. Imagine this is a seawall, and you have one of the waves going slosh and going right at the top, and the other one's going boom. It's like at a trough. Those two will go boom and cancel, and you'll see nothing there. Right? In light, that would be a black spot. It's an absence of anything. And other places, you'll have a high point, take another high point, and they'll hit each other right at the point they hit the seawall. What's going to happen when the 2 points hit each other, 2 high points? They go higher or lower? Higher. Higher. So that's going to be a maximum, meaning it's going to be brighter. So what you'll end up with then are these bands. Like this is a big bright band. Here's another one, here's another one, here's another one, here's another one. Simple. Right, that's what you expect. However, since quantum mechanics also predicts light behaves like a particle, we can try the same experiment, just like the guys did in the video, by shooting the light beam through one little bit at a time. It's like you opened up your flashlight and opened it for just a little nanosecond and let light come out. When you do so, if this light can't interfere with anything, you would expect the light to go, since it's just one photon of light, it can't interfere. So you would expect it to go through one hole and make a pattern, almost, that might look something like this. Imagine the light comes through one hole and goes, and leaves a little spot there. And I go, let another little photon out over here. It goes through one of the holes and makes a spot. Maybe it goes through this one this time. Leaves a spot on the screen right there. We do it over and over and over and over again. You would expect to see, just like shooting my machine gun bullet through 2 little holes in the wall, 2 piles like this. Does that make sense? If you're shooting particles, that's what you'd see. The problem is, and here it is, this is the whole guts. If you get this, you're at like 1920 and we're all in trouble. The pattern that you make looks like this, even if you shoot the photons through one at a time. You shoot a photon through it, it goes bump, and leaves a bump there. You wait a second, you shoot another photon through it, goes bump, leaves a bump there. The third one through it goes bump, bump, bump. And when you're finished, you wind up with the exact same pattern that you had as if you let all those photons go through at once and interfere with each other, like big waves. And so the idea then is, and here's the question, it's 1920. We're at one of the first conferences on quantum mechanics. People like Einstein are there, Schrodinger, Marie Curie, all the biggies. People like Heisenberg will be there by 1927, I think. And the question is, how can you make a system that has it where when you shoot photons one at a time through these slits, they make a pattern that looks like you shot a whole bunch of them at once, meaning like you got the interference pattern, so it looks like a wave. The question is it possible the photon is carrying something with it? That's kind of like making the interference happen. This is the exact same kind of thought process people had to go through in the 1920s to figure this out. What you are is very close to what's called the Bohm, B-O-H-M, pilot wave interpretation of quantum mechanics. The idea that there's some wave that's guiding the photon, like the photon's on a track, and that moves each photon to each place, and mathematically it works. Does it work? Sure. It's mathematically consistent, there's nothing wrong with it. This is what we're right at the edge of that point in quantum mechanics where we start talking about how there are different interpretations Have you heard this before? People go, oh, there's the such and such interpretation, the Copenhagen interpretation, or the Bohm interpretation. This is why you're getting different interpretations. Both of them are mathematically consistent. They give the same results on the screen. The question is, and the thing we can't access, is what happens between the lights, the slit, and the screen. What happens here? No one knows. Why? Because science deals with what you detect. It deals with what you observe. And no one's observing here to there. Right? Only when you get to the detector. So you can construct a mathematical formalism that works like that. There might not be real waves there. They are waves of what we would call probabilities. Meaning the waves themselves aren't composed of electrons. There's just a probability that propagates through space. And when you measure it, the electron goes and pops up into some place. How do you know the waves interfere? Observationally speaking, as a scientist, how would we know?
Right.
The only way and the closest thing, and it again is like, from a philosophical point of view, it is we observe the pattern on the screen and work backwards and go, all other waves in the world that we know make that pattern when they interfere.
So does particles.
Yes. So does that necessarily mean they're the same thing? No. They might just have the same property of interference. To give you an example, just because I eat my hot dog with relish and you eat your hamburger with relish makes them both taste like relish. It doesn't make hot dogs equal to hamburgers. In the same way, the quantum objects have the property of interference, we think, from what we observe. It does not make them the same thing as a water wave or an ocean wave or a wave in a slinky. This is what they had to get to. How about one guy over here?
Anything to do with entanglement and spooky action at a distance?
Yes. Well, the entanglement is the idea that the particles' wave functions are mixed up with each other, which is going to give, like, if you launch two particles and let them interact with each other and then separate, their quantum mechanical probabilities are entangled, meaning what you see for one over here will affect what you see for the other. Let's take a really quick example of this because I know people, how many people have heard of spooky action at a distance before? Okay. It's a very common one. Easy example. Let's say I have a 2-photon process where I have a crystal that I excite. I take the crystal and I hit it with something. And so it's going to give off 2 photons of light. And one's going to go this way, and one's going to go this way. And as they do, I automatically know that the photon that goes off this way has what we call a polarization, meaning it shakes like this, vertically. Polarization in the photons is a conserved quantity. What that means is if the first photon shakes like this, the second one shakes the opposite, goes horizontal. As it travels, they're doing this. And so the point is, but the problem is until you measure it, there is no way to tell which one's the up-down and which one's the horizontal. And so the problem is, we can prove mathematically, this is one of those weird things. And this is actually 2 slides ahead, but we'll cover it for now, I guess, since we're already here. You can prove mathematically that before you measure it, the particles don't know themselves which one they're in. They're like this, they're neither one. And then you get them out here and you measure this one, you go, pop, measure it. And they put it on a detector, and it goes, boom, I'm going to be the up-down. What does this guy have to become? Yeah, the side to side. Now, how in the world did this guy know what this guy became? No one knows. That's why we call it spooky action at a distance. Now, of course, the little smarty smarts among you might be saying things like, maybe I could use this to make my superluminal communications device and send signals to Pluto. Meaning that if I could do what I want to do to this one has to respond instantly. There's only one problem. Can I control which state this one jumps into when I measure it? Can I make it become this? No. There is no physically known process that we can make it become this or this.
Well, how does
when I measure it becomes one.
detector work?
The detector interacts with it, and then quantum mechanically it becomes one. The interaction is what makes it do this, but we can't control which one it becomes. You know, that's very careful. There's a difference between detecting it, meaning making it jump to a state, and deciding, hey, I want the up-down. No, I want the left-right.
But what, like, how does the detector work? Like,
Oh.
you detect it via radiation, or like, how does...
Most of the time, if it's something like light, it's going to be some material that when the light hits it, it's going to excite electrons in the material, which will change either a voltage or a magnetic field, or the electrons will start to move and make a photocurrent, so we can measure that in a wire. So what's happening if you zoom way down, you see protons and electrons. The light beam comes in like this, smacks into the electron, goes, boop, I'm going to be an up-down, and that does something to that atom that makes up the detector. The detector itself is made of a material that we interact with. Yes?
I have 3 questions, actually.
Okay, if you want to just one, we'll get you to 3. But I got to get like a pile of
The
people.
first question
Give me one.
what is the margin of error in the devices used to measure
Oof, good
all this
question.
stuff?
Originally, they were really big. Like originally, I remember but now we can machine them like down to like, I remember being something like, we can do them with polarizers, and those are only a few atoms thick. Like we can use those like slits now, and Polaroid strips. They're long chain molecules that when you excite them, they do something. And so we can get those down now to single photon processes. Like the one you saw in the movie, that's measuring one photon at a time with a very sensitive detector where each atom can pick something up. In the beginning, it was ridiculous. I mean, you know, it's just kind of like, I don't know, what's wrong with that wall? A lot's changed since 1920. Yeah, the question basically is, why is it that quantum mechanical things can spread out and go between two slits, but we can't do it? I can't make myself run through that door and that door. I can try. It's going to be the last lecture ever. Let me show you how I extrapolate this to the macroscopic world, and you'll see why this happens. A guy named Louis de Broglie, 1924, as a young PhD student, has a really cool idea. He says, this is the case that only photons of light behave like both particles and waves. Because up until 1924, they thought that things like matter, like electrons and protons, were particles, just like that, and that was it. Right? And so by 1924, Louis de Broglie goes, hey, I've got an idea. What if I also say that electrons can be particles or waves? Writes a PhD thesis out of it. I was just looking at it today. The section that like actually discusses this is really small. It's only a few pages. The rest of it's all background. And so the point is that he writes up this dissertation very quickly. To give you an idea, his whole dissertation was like 84 pages. That's all the background and everything you want. Mine was like 320. You know, so he gets it really easy. I guess it's the easiest thing in the world, but it's a really cool idea. So he gives it to the committee, and they go, what do you think? The committee goes, this is pretty weird. And so they send it to Albert Einstein, because they're going, this is so strange, I have to send it to him to see. Einstein goes, that's a good idea. Give him the PhD. He wins the Nobel Prize for it. De Broglie, not Einstein. Yeah, just for fact-checking the document, we gave him another Nobel Prize. And so the idea that Louis de Broglie comes up with is that matter is also acts like a particle in a wave. An electron doesn't just look like that. Well, it doesn't look like a little sphere. That's what you see in your science books. But if you actually check out, you know, you've probably seen like, you know, in your college chemistry books, they'll show these electron clouds. You know what I'm talking about? They'll show like a sphere, and it's like, well, it's a cloud region. The reason it's a cloud region is because that's a wave that's moving around there, wrapped around your nucleus. But the idea then is all moving objects have a wavelength called the de Broglie wavelength. That's how long their wave is. The problem is, if you look at it for humans and you calculate it, it's like smaller than the size of an atom. If you tried to cram us through a hole that was like one atom thick, you'd just go and splatter on a wall. But the problem is, you can't see it quantum mechanically at a macroscopic scale because our wavelength is so tiny you can't observe it. As the objects get bigger and bigger, the quantum wavelength gets smaller and smaller. And that's why when we talk about, say, an electron or a photon, things like the wave nature make a really big difference. But the bigger the object is, the wave becomes smaller and smaller. So it's like the universe hides the quantums behind the size of objects. An easy example of this, we call it the microscopic regime, meaning stuff that's quantum mechanical. At the top, we'll call it the macroscopic regime. In the middle, we call it the mesoscopic regime, meaning it's the region where you kind of see some quantum mechanical stuff, but sometimes you don't. The biggest object I've ever seen that actually displays quantum mechanical behavior is DNA. You ever work with DNA, there are pi bonds between the bases. They have like A, C, G, and T, and they're in some sugar phosphate backbone. Those bases sit right next to each other, and there's what's called a pi bond in there. And that pi bond keeps the thing stable. Without it, the system would fall apart a lot faster. And so that pi bond displays quantum mechanical behavior in DNA. That's the biggest thing I've ever seen. If it were classical, if you do the classical numbers with it to actually get out the answer, the bond isn't stable. It's stable because it's just at the right size to be mesoscopic. It's in between microscopic and macroscopic. To put it simply, imagine a box with one electron in it. It looks like a wave, right? Now I throw another electron in. What happens to the wavelength according to what I just said? It gets smaller. So you can imagine the whole system that's kind of like a wave, now it's kind of shrunk up into the middle someplace. I throw some more electrons in it. Every electron I throw in, the wave gets smaller and smaller and smaller and smaller, until eventually you wind up with a clump of electrons and they look like particles because the wavelength is so small you can't see it. There's no way to detect it. There's no detector that would measure it. And so the more stuff you throw in, the smaller the wavelength becomes. This is why the quantum mechanical nature of the world is hidden from us, why we don't see disks behaving like waves. Because they're made up of trillions of interacting particles. If I strip off one electron from that thing and take it and isolate it, throw it in a box, sure enough, it becomes a wave. Smears out. Hidden variables, for those of you who don't know. is what Einstein subscribed to in quantum mechanics. He held this viewpoint and he said, look, there must be something. For example, this spooky action at a distance. The idea that I separate the two photons, I measure one, it goes, oh, I'm this way, and the other one goes, I'm that way. He said that's not possible. There must be some variable, something underneath the system that's transmitting information. For example, you could say that our quantum mechanical equations describe what's happening, but there's something else underneath it that's going on that we can't detect yet. Maybe we need a better detector. Maybe we need a better mathematical formalism. Whatever it is, it's some variable that we're not accounting for. Right? This is what would be known as the hidden variables interpretation of quantum mechanics. This is put to the test in what's called Bell's inequality. In this inequality, imagine for a moment, I'm going to take this bottle. How's your pad? Now, quantum mechanically, if I take this bottle and I put it behind this thing, when nothing's observing it, I'm observing it, obviously. But let's assume that no one's interacting with it and it's not being observed. Quantum mechanically, this localized object, meaning the bottle of water, starts to smear out, become like a wave. Okay. And then when it interacts with something, all of a sudden it goes whoop, and becomes like a particle again. It becomes something I can see. Okay. And so the question is, if I take this, oh, now you see the bottle, right? Now it's spread out. Here's the fundamental question. Philosophy nerds, here it comes. Is the bottle really there before I take away the binder? Or is the bottle spread out and jumps into one place when I take away the binder? This question is just like the hidden variables question. Is there something going on behind the scenes, or is the bottle really there the whole time and we just haven't looked at it? Do you see what I mean? And you see how there's no way to tell the difference between the two ideas? You know, I don't know, is the bottle smeared out? I don't know, I can't look at it. How could I tell you? So a reasonable scientist would say, it's not in the domain of something we can observe or test, therefore it doesn't count. We remain, you know, we just don't know on that question. The problem is a guy named John Bell in 1969 proposed a thing called Bell's inequality, where he said we can experimentally tell the difference as to whether or not the bottle is really behind the screen all the time, and just you can see it, or whether it smears out like a wave behind the screen, and then when you move the screen, it goes whoop, and jumps into one place. This is an experimental, testable, Peter wants to write something down. This is an experimentally verifiable, testable, and therefore scientific idea. A guy named Alan Aspect in 1981 actually performed that experiment for the first time, and has been performed thousands of times since. And the conclusion is very clear in every single case. The bottle is not there until you pull away something to look at it. Think of, I know, he just got it. This guy right here just went, what? That's wrong. This is why it's weird. This means that in the absence of an interaction, the whole world is smeared out like a wave, and then when something interacts with it, like a beam of light, they go, whoop, and they'll jump into one place. Make it an electron, make it simple. The electron's moving around, and there's nothing interacting with it, and all of a sudden the light beam goes on it, and it goes from being smeared out all over the place, like a wave of probability, to going and popping into one spot, and there's your electron. Just like what we see on the screen. It's smeared out like waves of probability until it hits the screen, and as soon as it does, it goes, bam, and jumps into one place, and that's the dot that you see. The photon was not moving around like a particle the whole time. It was a smeared out wave. I still don't believe, I know, I'm saying, well, that can't be right. But I've done the math, and I even can't believe it's right. But it is. Why, and here comes the point, think about this very carefully, especially you philo kids. Why can't you believe that idea? If you're like me, it's because you've never had direct experience with it. We rely as humans so much on what we experience. I see this all the time in physics classes. I'll tell the students, when I ask you what happens here, your first thing you're going to say is, you're going to think about it and go, what happens if I run across ice, say for a frictionless surface? And they'll imagine it. But then very quickly we started getting into things in physics that people have no intuition for, because they've never experienced them. Things like statistical mechanics of particles, quantum mechanics, general relativity. Things they've never seen, they've never been like a massive gravitational body. And I tell myself, you know, fat joke or something. Not that massive gravitational body. And the point is, without an intuition, your brain goes, that's all right. Because it seems to defy your intuition, right? I have like 3 or 4 people waiting. This guy waited for 5 minutes. Yes, sir.
So, okay, so then on a macroscopic level, things also behave as either particles and waves. That's the 4th bullet point there. So by that same reasoning, then, when we are alone by ourselves and not under observation, does that mean we are waves with the illusion because of consciousness that we're particulate?
Okay. This gets into what's called the Schrodinger's cat paradox. You guys, how many people have heard of this before? No? Okay. Schrodinger is a sadist. He has a cat called Schrodinger's cat, very unoriginal name. He puts a cat inside of a box, completely seals it off from the outside world. He puts a vial of poison in it that's going to kill the cat. And then he puts a little hammer that's going to break the glass, let the poison out, and kill the cat. However, the trigger, the hammer, is only set off if this certain atom decays. It's a radioactive decay or something like uranium or whatever you want to use. And it's going to decay radioactively and hit into the detector. If it hits the detector, the hammer goes off, breaks the poison, kills the cat. If the particle does not decay, nothing happens. The cat's alive, right? And so by extension, you wait a while and you go, what's the probability that this particle has decayed? And you go, it's 50%. That means that there's a 50% chance that the cat was killed and a 50% chance that the cat was not killed. The problem is, quantum mechanically, since you haven't observed it yet by interacting with it, you cannot say that the cat is alive or the cat is dead. The cat is in what we call a superposition. The cat is both alive and dead at the same time. I know, the guy in the white shirt's like, that sounds like he's making it up. I'm not making it up, I promise you. So anyway, that sounds like nonsense again. Guys, not my cue. I didn't do it. The problem is that the cat, and this is what Schrodinger's objection in the beginning of quantum mechanics, you know, some of the big debates was, how could you get around this kind of thing? Because you go, well, what counts as an observer? Supposedly, according to Schrodinger's cat, when you open up the box top, you've interacted with the cat. And now it'll jump into being alive or being dead. You know, wait a minute, what if I put a camera in the box? And let it run, and the camera's recording right there. I open up the box, and I pull it out. Did the camera just suddenly reinstate all of its memories into the past when the cat actually died like an hour before? That sounds so silly. The reason that doesn't work is because the cat is a macroscopic entity. Remember we talked about how you lose the quantum mechanicalness the bigger the system is? The cat has trillions of particles that are allowed to interact with each other. Thereby the cat doesn't act like a quantum mechanical object. You have to, if you would isolate the system and have like just an electron in the box, that would be a quantum mechanical thing. It would be a mixture of electrons that's alive and dead, I guess. But anything, the bigger you put the system there, if it's a human or a cat or whatever you want, it's big. The system interacts with things. Schrodinger never took this into account because the formalism hadn't accounted for it yet when he created this argument. It hadn't accounted for the idea that the quantum mechanicalness of the world is lost as you make the system bigger, meaning it has more pieces to it.
What about what you said about the water bottle?
The what?
The water bottle.
Oh, yes. That would work. Okay, I'm sorry. I probably went too far by using a water bottle. I should have made the water bottle an electron. Absolutely, because the water is made up of trillions of molecules that are echoing themselves. That's pretty soon you're all going to go home and be thinking that like the ocean doesn't exist if no one's sitting on it. Which sounds crazy, but that's the thing. If you're not careful, you fall into this kind of trap and go, wait a minute, no one's in the ocean today. How is there anything out there? You know, it's like a Twilight Zone episode or something.
Then they finally answered the question that if a tree falls in the forest,
there's no tree. The tree is there and not there. No. The point is that because these aren't quantum-sized objects, you don't see that behavior. The classical world is like this big tapestry where I pull away and all the quantum interactions are happening and getting rid of the quantumness as I zoom away and make bigger and bigger systems of objects. If it were just an electron, then you'd actually see it would be a mixture of both. So you did a measurement. Yes, sir. Peter.
How do we know that all of this isn't a matter of just our limitations of human perception?
We don't.
It's just a matter of our senses being too faulty to pick up on what's actually happening.
Not a bad idea. There are questions in this that frankly are beyond my knowledge base. You know, there are people I know that work in what are called category theory mathematics. It's this really abstract branch. I have a couple of nerdy friends who never come out of their basement and work on this all the time. And this is the kind of stuff they talk about. They talk about foundational issues in quantum theory. And you sit there and go, well, what would it be like if there was a problem with my perceptions? You know, would I need a more sensitive measuring device? We extend our measurements all the time to things we don't directly perceive, don't we? I can only perceive the visible light in this room. Yet I can put a thermal camera in here and I can see infrared light. You know, or I can put a gamma ray detector in here and I can see the gamma rays. Well, hopefully not to kill us all. But if there were gamma rays, you'd see it. I can put an antenna in here and turn on my radio and see, quote unquote, radio waves. So we regularly extend our measuring abilities beyond our direct perceptions into smaller and different realms by using clever devices. And so there's nothing wrong with the question. The question's always a good one, right? If we're measuring something, what are the limits of the measurement? The problem becomes then you go, and this is why I tell my 125 students, this is why we put error bars in place. Every measurement has a limit to how certain it is, based upon what you measured it with. Think about that. If you use a better measurement device, you get a better measurement. Right? So is it possible to have limits? Absolutely, and they're built into the idea. Because that's just a fundamental limit of how close we can get to it. This is what you guys are used to seeing, nucleus and electron. I remember I was maybe a 7th grader. I was always kind of a science nerdy kid, and got beat up for it all the time. And so I remember sitting there thinking, the center of an atom is made up of protons. And the stuff going around the nucleus is made up of electrons. And so those charges are opposites. What do opposites do? Attract. Why don't the electrons just fall on top of the nucleus and be done with it? The reason that electrons don't fall into the nucleus is because think of the electrons as being a wave instead of being a particle. If the electrons are a wave, they're going to have some specific wavelength, like a violin string. So imagine, for example, this is a wave. Now, if this were a piece of paper and I turned it and wrapped it onto itself, you would expect this piece of the wave has to touch that piece of the wave to make it stable. If not, you're going to have something where you have part of the wave up here and it can't intersect this guy. And so this is just a rule. And for any, it's like standing waves for any of you do anything in music. And so the idea then is this piece of paper, this strip, if I wrapped it around and made it intersect itself, it's only stable if this thing touches that thing. And so in order to do this, if I wrap these around the nucleus, they can only exist at certain distances. Otherwise, they aren't stable. Meaning this guy here doesn't touch, it would touch like up here, and it doesn't let it do that. The only universe lets it hold is if this end hits at the same place as this end, like on the middle. What does this mean then? This means that the electrons only exist at certain distances away from the nucleus, because that's where these, what we call stable standing waves, exist. And so this is what an atom would look like. You imagine the electrons being a wave instead of a particle. There's a bunch of these little strips where the probability wave is moving around and it has to intersect itself at the same place. This would be your closest orbital, right here. Here's the next one, this is what we call the n equals 2 orbital. Second one out, n equals 3, n equals 4. This is what gives rise to the atomic structure that you see now. Think about it this way. Why do the electrons only exist at a certain distance from the nucleus? Why not in between? They exist here or here. You've heard it's like a quantum leap. A particle absorbs some energy and goes poof and jumps up to a different place. Why that place? Why not somewhere in between? That's because it's the only places where the stable waves exist, the stable wave pattern. And so the only way to get to this conclusion is to think of the electron as being like a wave instead of being like a particle. This is a very clear and big consequence. It proves that things like the orbitals of, say, hydrogen here are the same as we would find as the orbitals of hydrogen way out in outer space. This is important because when we want to do astronomy, a lot of stuff we look at, we can't go to. I can't send a spacecraft out the other side of the galaxy. How are you going to measure anything? And so one of the big questions is, how would you know? Fortunately, because we, at least so far as I can tell, the laws of the universe work the same everywhere. The hydrogen stable orbits here will be the same as the stable hydrogen orbits there. And so I can do experiments based upon the light that comes from that hydrogen. How's that? Are we still in the same place? You can tell people are fading away. You all right? Wake up, come on, sit up. I was like, no, I'm not going to sit up. Yes?
Part of that is why atoms with the same amount of electrons act similarly.
That is the reason why. Why is it every electron and every, say, helium atom, why are the electrons always placed right at the same distance in every helium electron in the universe? Why wouldn't they be in different places? That's why. The Schrodinger wave, or the de Broglie wavelength of the electrons are always the same. And so where they can be stable around the nucleus is always the same. I haven't heard from you yet. Yes?
How does the octet principle of electrons tie with the stable wave?
What are you guys, a whole bunch of little science majors? Oh my goodness, good question. Stable orbitals come from this with a combination of the Pauli exclusion principle. For those of you who don't remember, the Pauli exclusion principle states that you can only have 2 electrons in any existing orbital, which is why all your numbers can be like 2s or multiples. But what's strange is, I had always thought that the reason the Pauli exclusion principle existed, all the way until grad school I thought was, that the reason the Pauli exclusion principle existed was because there were 2 electrons, and the electrons don't like each other, so they repel, and that's why they're stuck that way. That's not true. It's any 2 what we call fermions, which are a particular type of particle. This means certain particles that even don't have a charge, you can put some neutral fermions in there, and they still will fill up and go, I don't like this. The reason for this at the bottom of the world comes down to the fact that the quantum wave functions, we talk about as wave functions, mean probability waves. The probability waves that describe these particles naturally repel each other, not because of charge, just because of the way the wave function is constructed. This is a very hard thing to grasp because you don't see any reason for it. Why should there be that repulsion between the wave functions? I get the two waves near each other, they go, no, I don't like that, go away. And they won't let more than two into an orbital. How can that possibly be? No one knows. At the bottom, it works that way because we mathematically described it that way. Is it possible there's some deeper fundamental idea as to why that's happening? Sure. We call it things like string theory. You guys ever heard of string theory? Right? Areas like this, or what's called loop quantum gravity is an alternative idea. And so these things try to describe everything as being little vibrating bits of string. Is it right? We don't know. We don't have a particle detector big enough to test it. I once read that to test string theory, you need a particle detector about the size of our solar system. We can't get people to even fund NASA. Are you kidding? Trying to build a particle detector the size of the solar system is going to have to wait a few thousand years. The professor, I'm in trouble.
No.
Here it comes.
Isn't there an interpretation of quantum mechanics that says one of the reasons why at the macro level we don't see the quantum effect and the wave collapses is because all the interacting particles are acting as observers?
Yes, that was what I was saying about as you add more stuff, the interactions count as observations themselves.
It's I wasn't crazy.
No, not at all. Crazy like a fox, maybe, but not crazy. Yes, sir. Number 3!
If probability is a representation of potential, how much of our knowledge of these particles is actual versus potential? Basically, I'm asking how much of our knowledge is actually do we know about the identity of these particles versus the potential? It sounds like a lot of knowledge is probabilistic at best.
Yeah, I would say at the bottom of the world, until you actually do the interaction, all of it is what you were saying is potential. The first thing is, this is what we were kind of getting into with the hidden variables idea. At the bottom of the world, the electron is some probability wave that's moving through space. And you go, where's the electron going to pop up at? Well, it depends on where you're looking at on the probability wave. If you're looking at, let's say, this thing on the right is my probability wave. Now, to measure something in quantum mechanics, you actually take it square. Meaning, if I looked at this, there's a very high chance, this is all in one dimension, this is just the x-axis. So there's a very high chance the particle's going to pop up there when I do a measurement. There's a very high chance it's going to pop up here. There is no chance it'll pop up there because you're at 0. When you try to look at where the particle is there, you'll never find it. If you measure the particle, there's a reasonably high chance it might pop up there, a pretty low chance it'll pop up there, a really low chance it'll pop up there. Okay? So before you measure it, all you see is a probability wave. And when you interact with it, the particle pops into some place described by that probability. And so the question is, should we understand these things better? Of course. The problem is we don't know how. Is there something, the fundamental question that we're all kind of banging around on this, is there something deeper that makes those probabilities come into existence, like string theory? Or are the fundamental probabilities themselves just the bottom of the world and we don't want to accept it because we're used to everything being macroscopic and well-determined? No one knows. Because there is no one experiment that would tell you that answer. At least not right now. You can find one, absolutely. This is what people that currently do research in this kind of thing are looking for. Now, most of the people I've seen that do work in things like some of the applications we can talk about, like quantum cryptography or quantum computation, are using quantum mechanics in this form. They aren't trying to do anything deeper, like get to a better understanding of quantum mechanics at a fundamental level. They're doing more engineering work, meaning how can I use these rules of quantum mechanics and the strange probability stuff to give me stuff that I wouldn't get, at a macroscopic level, like special computers that may have single electrons. Okay? And so in that sense, that's more of an engineering issue than I would say a fundamental knowledge issue. But the question's a great one. The problem is how would we broach it? And since the 50s, they've still been fighting this. Einstein would not accept that probability was the bottom line. He died still believing that there was something underneath that was deeper.
Seems like most of the effort is geared towards the probabilistic side rather than the definite side.
Definitely. We would call this the Copenhagen interpretation. The Copenhagen interpretation of quantum mechanics says the math works, use it. Don't worry about the rest. That's really what it says. It's kind of like, look, why does this work? Because it works. It describes reality. And the only thing you can talk about is the stuff you can actually observe. As you go deeper, by all means go deeper. As we've seen, you can construct any number of mathematically consistent theories, like the pilot wave interpretation. Yes, sir?
Didn't some of John Bell's experiments prove that it was impossible to know?
John Bell's experiment showed that the hidden variables was not the case. There wasn't something underneath it deeper, that it really wasn't there until you measured it. The problem is that you ask, why isn't it there until I measure it? What makes the probability wave what it is? That question still has no answer. So far, it's been completely descriptive, not explanatory. The chief has a question.
Let me pose a question and answer it, and then correct me if I'm wrong. So the question is, I've always wondered about, with regard to probability waves, are they simply really clever mathematical tricks that physicists use to predict very accurately, probabilistically, where certain particles are likely to be, or is the probability wave, is it an actual thing? Is it some sort of physical system that we don't understand that affects where a particle is likely to be? And my answer would be, and correct me if I'm wrong, we're really not entitled to know at this point. We can't really say whether the wave function is something real, something physical, or it's simply just really clever mathematics that does a lot of work for us.
I agree. We can definitively say let's say I'm looking at the probability wave thing up there, for where to find an electron along the line. I can say definitively the electron is not there until you measure it. It's not like it was sitting there all along, and I went, boop, and measured it, and went, oh, there it is. I can definitively say the electron is not there. I can definitively say the probability wave accurately describes where the electron will show up. What I cannot say is whether or not the probability wave A comes from some deeper reality, like what gives the probability waves its structure in the first place, or B is some real thing physically, because there's nothing that we can do to measure it. Is it just a mathematical construct, or is it something different that's actually there, but is beyond measurement? Right? There's no physical test. Scientifically, there's no what we would call criteria of falsification to prove it wrong. So therefore, there is no answer. I mean, the question is, well, for intents and purposes, agnostic. We just can't know. There are tons of cool things that come out of quantum mechanics. I will mention just a few quickly. The structure of white dwarf stars, for example. This is the white dwarf. It's kind of hard to see from back there. The white dwarf is in the foreground of these two. It's that one. That is a white dwarf star. This is a star that is blown off its outer layers near the end of its lifetime. And as it does so, it leaves behind a remnant that's slowly cooling down over the course of billions of years. And the point is, before quantum mechanics, we didn't know white dwarfs were stable. We didn't know how to make them stable. The reason white dwarfs are stable is because of what you see on the left, what we would call degenerate matter. In regular matter, something like what we see over here, protons with a bunch of electrons going around them, these would be the electron energies. This is like looking at a side view of this. Let's say I just have a whole bunch of electrons going around. Make more electrons. Now I have lithium. And so this is what I'm looking at. I'm looking at the side view, like these guys here. I'm looking at the electrons. I'm looking at like the protons would be down here. So I'm looking at the electrons being able to jump up and down as they absorb and emit energy. The problem is, in a white dwarf star, the gravity has compressed everything so much that the electrons are crunched down on top of each other and create this stuff called degenerate matter, where literally, because the only reason this thing doesn't implode on itself and collapse completely is because of the Pauli exclusion principle. The idea that you can only have two of these electrons in any one shell. And so they all go, crunch, I'm going to get right on top of it, and I'm going to fall in on myself. Without the Pauli exclusion principle in quantum mechanics, white dwarf stars, we couldn't explain how they're still stable. Like, why are they propping themselves up against gravity at all? Shouldn't they just fall in on themselves and make black holes? And so white dwarfs are stable only because the Pauli exclusion principle is making these guys go, I don't like that, get out of here. They're trying to push away from each other. That's the only thing keeping the star from imploding entirely. Right? Which means we got kind of lucky. Like, you think about the historical timeline. We discovered quantum mechanics right as modern astronomy started really taking off with better telescopes. Imagine if we discovered white dwarf stars and no one had figured out quantum mechanics yet. We'd have to go, I don't know, you'd have to wait until quantum mechanics caught up to explain how the white dwarf is stable in the first place. This degenerate gas doesn't exist in classical physics. It only exists quantum mechanically. Actually, let's use an easy one. Tunneling diodes in most electronics today rely upon quantum mechanics. And what happens is we put an electron voltage on one side of the device where you have electrons going at something, and there's this thing called what we call a potential energy barrier, meaning we put a gap between two things so the electrons don't want to go over. In classical physics, this thing called a tunneling diode doesn't exist. There's no way to make it work. If you took a tunneling diode that uses all of your electrons today and took it back to 1800, they couldn't figure it out. Give them a microscope, give them all the tools, they wouldn't be able to figure it out. They'd have to rediscover quantum mechanics to know how that tunneling diode works in your electronics today. How an easy one. I know you guys are all really fond of lasers because y'all love your DVDs and your Blu-rays. Lasers don't work without quantum mechanics. You have to describe how photons are emitted from atoms and how we can get them all to work at the same time. Meaning I get all the electrons in the substance. Let's take an easy one, a helium neon laser. Put helium and neon in and you excite it a couple different ways. One way is electrically by putting a current through it. And all the electrons go, hey, boom, they all jump up to a higher energy state. And you hit them at just the right time and you trigger them with something. They all go whoop, and fall down at the same time and give out this big pulse of coherent light called a laser. That idea didn't exist without quantum mechanics to describe how what we call population inversion works. You get all the electrons to jump at the same time. It's like you're getting the whole room to jump up and then drop back down together. It doesn't work in classical mechanics. Another one is there's a special type of chip used in computers called a SQUID chip. It stands for semiconducting quantum interference device. It's very ubiquitous in computers today. Same thing, doesn't exist without quantum mechanics.
What is it called?
The SQUID. Semiconducting quantum interference device. Let's see, I got some more. Let me think. More applications. How about, I'm trying to think of some more that are pretty straightforward. Well, I guess we do quantum computers right now. Quantum computers are a really big one. Actually, I'll do one more that's a little, because it's already here on the market. You guys ever heard of quantum dots? How many people have heard of the word quantum dots? Okay. Quantum dots are the idea that we can trap inside an individual atom electrons exactly where we want them. And by modifying where those electrons are, by changing how much potential energy is there, we can modify the properties of the atom by making the electron change. The orbits are where they are because of all those interactions. Imagine I had the ability to put electricity or something and change the interactions so the quantum dot would change shape. This was first found in TVs that have been released in 2013. For the first time in the history of the world, you can find quantum dots in television. They were never around until 2013. Very first ones. And pretty soon, I think within like 15 years, you'll have TVs that have pixels that are so tiny they're the size of individual atoms as emitters, which means you won't be able to tell the difference between a TV and real life. I can put one up on your wall and you're going to think it's a window. You know, I'm dying for that day because we're going to do so many practical jokes. You know, walking into stuff, you know, it's going to be so much fun. I'm waiting for it. It's going to happen. You watch, you told you first. You know, how many people have heard of quantum computers? Quantum computation? Okay. In a quantum computer, we use bits as ones and zeros in regular computers. Computers use a thing called qubits, not CU like the measurements. QUBIT. A qubit is a quantum bit, where something is in a mixture of 0 and 1 until you do the measurement. And so there's this rule in information theory. Rule 1 is information is physical. It has to be represented in something. You can't just say information is there. It has to be bits of oxide on a hard drive, or it has to be letters in a book. It has to be something physical for you to look at to interpret. And so in quantum information, we encode things like ones and zeros in the spin of an electron, meaning spin up or spin down. Now, if this is a spin up, meaning it's a 1. If it's a 0, it's going to be a spin down. The problem is until you actually do the measurement, it's in between them. Yeah, it's not there until you measure it. So that is what we would call a qubit. It's a superposition of 1 and 0. The point of this is, if you put very clever people put algorithms in these things, and they go, that means I can do all the possible computations at once. This sounds like it's kind of, you're going, who cares? I don't care about that. This is really useful for certain applications. For example, things like solving computationally hard problems. An easy one, the reason, okay, do you guys know who DARPA is? The Defense Advanced Research Projects Agency. They invented things like the internet and the GPS system. They dump money every year. I was at a conference at Caltech a few years ago, and they were all there. And they dump piles of money into quantum computers because whoever gets them first can break everybody else's codes in the world. Every cryptographic cipher. They want it so badly.
You can make a skeleton key out of that for any classical
computer. It is. Any classical computer, you can emulate any classical computer on a quantum computer exponentially faster. It's beautiful. The hard part is a truck drives by outside and the quantum computer decoheres. It counts as a measurement. So you're going, well, how am I going to isolate this so it's stable, so it isn't going to let it run the computation for a few minutes to get it done. So factoring large numbers would be a big one. Factoring large numbers is the big thing people do. Why? Because they know if they can do that, they can do other hard problems that people can map to those. They're very similar in terms of structure, right? And so easy applications, if we could build a classical computer, build a quantum computer and make it emulate a super big classical computer, things like protein folding in biology. We want to know all the ways to fold these proteins because it can tell us about diseases. And so you're going to let classical computers take, I've been at the UCSD, they have everybody ever been to the supercomputer center at UC San Diego? The thing's ridiculous. It looks like they have Battlestar Galactica. It's like bigger than this building, and it's just rows and rows of servers and a giant dish on top of the building, just in case you were confused about what they did there. I don't know what the dish is for. I guess it beams up the space. Imagine building a quantum computer that is exponentially faster, and so it can do all the protein folding for you like that. And so that's the kind of stuff that they work on right now to do this stuff. How does the Higgs field? Have you guys heard of the discovery of the Higgs boson at the Large Hadron Collider CERN? How does the Higgs field fit into this picture? This deals with quantum mechanics at a level of things like the 1920s. Right? If you move forward through like the 1950s, they've reasonably well figured out quantum mechanics. But then particle physics starts to kind of take over this area of research. And there's this question of things like, just until like 2009, they didn't know this. 9, 10, something like that. Trying to know, for example, we figured out what antimatter was, like in the 1930s. We figured that all particles had antimatter equivalents. For example, for an electron, you have this thing called a positron, that they intersect, and boom, they'll annihilate by E equals mc squared. Right? And so the 30s and 40s was this time in particle physics of finding all these extra particles, and pretty much filling in the particle family tree. They had all this big family tree. This particle has this antiparticle, this particle has this antiparticle, and they'll sit there and slam stuff together in the particle accelerator as fast as they could, look at the shower of garbage that came out, and pretty much try to reconstruct the watch by looking at all the little strings that they got out of the bits. That's what it literally is. They take all the junk and they go, this works backwards, and that means it was given off a positron. And so then, once you go, we've got these particle families filled in, which happened up to like probably the 80s. Then people started going, why do the particles exist at all? Why do the particles have the masses they do? Why is the mass of an electron what it is? Why shouldn't it be something else? For historically, we just kind of went, that's just the way it is. The idea was formulated that this thing called the Higgs field, which is this, it's kind of like Star Wars. It's like this field that permeates all space. The Higgs field at high energies is what gives particles the masses they have in the early universe in the first place. If the Higgs field had different values, you would see, imagine some alternate universe where the Higgs field was a different number. It would give rise to particles that have different fundamental numbers, like different charges on the electron or different masses of a proton. Right? And so the problem is, to see the Higgs field, you have to make particles spin so close to the speed of light that there are energies that you would have found in the first few fractions of a second after the universe started exploding from the Big Bang. And so this is what they do at the LHC. They take 4 million particles a second of protons and antiprotons, put them in this big magnetic field, or big magnetic beam line that's like 27 kilometers around, and go poof, 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 and spin them really close to the speed of light, get them up to like 99.999% of the speed of light, and go, bam, slam them together, watch the watch comes apart, makes a bunch of springs, measure the springs with your detector, and work backwards. The simple and obvious question that I've wondered about for a long time until I got into college, if you can get them up to 99.999% of the speed of light, why didn't we just put an extra $10,000 in and get them up to 100% of the speed of light? Anybody know the answer? It's not possible because of who? Einstein's relativity says you can't get to the speed of light. You go up to 99.99, you put more energy to get to 99.999. More energy, 99.9999. You'll never hit the speed of light. It can't be done. Because I used to wonder, when I was like a little kid, I'd read about these things and go, you're like 99% of the speed of light. I'm like, you couldn't have spent an extra $1,000 and gotten to 100. Government spending sucks. Took a long time before I figured that out. The question was, why is it that if we have both matter and antimatter, why is there more matter than antimatter? Shouldn't you expect, you can imagine this world where, why don't we have the same amount of both running around? And you can actually calculate, you go back to the Big Bang, in the primordial balance of things. There were 10 to the 5th, meaning 10,000 particles of things like electrons formed for every one particle of antimatter. You're going, well, wait a minute, that's a whole lot more. Why is that? This is the thing that wasn't settled until, Don, do you know the year this was at 2010 that they figured that out? I can't remember. I think it was 2010, why there's an asymmetry. Because I remember being maybe I was in high school. Yeah, I was in high school. So like in the mid 80s, like the 90s. And I remember distinctly reading books talking about the possibility that they thought at one point that maybe whole galaxies out there were made of antimatter, and just because they hadn't collided with a matter galaxy, but if they did, it'd go boom, and you'd blow up two galaxies. It would be incredible. And so, because no one knew why there wasn't a bunch of antimatter, but there's a bunch of matter. And the point is, there's an asymmetry in the Higgs field that is what creates that exact phenomenon. That was not even known. When I started teaching, like, I don't know, a long time ago, like 10 or 15 years ago, it wasn't known. It wasn't known until I think 2010 was the year I think they discovered that. And they did it, same thing. They got the particles up to a really high speed, could see the Higgs field, and they found the asymmetry, that you get much, much more regular particles, you get few antimatter particles. The chief wants to answer.
I don't know if this addresses your question at all, but just having, as a layperson, I'm not a physicist, having read Brian Greene, he points out that, one way of thinking about the Big Bang is it's not the event that created the universe, it's an event that occurred in a pre-existing universe. Because, you're more qualified than I, but the laws of physics only take us so far back.
Yeah.
And so we can't really describe the moment of the bang. Energies are too high, and so there's a big question mark there. So that's my layperson's understanding.
How could the universe, like there's this one, who's the guy? Lawrence Krauss, the guy from the Origins Project at Arizona State. Wrote a book called The Universe from Nothing, like last year. And it was about how you could have closed time. So you go, well, how can you have a universe come from nothing, right, in the first place? Now, I can tell you the philosophical answer to this. I haven't even read Lawrence Krauss's book, but I know, like, from a philosophical point of view, some of the ideas on it. You're all philo nerds, right? Immanuel Kant, right? Critique of Pure Reason. The idea that space and time are like a picture frame through which our brain perceives the universe. And so to ask us what happens, quote, end quote, before the Big Bang is a nonsensical question. It's like asking what was before the beginning of the cassette tape. Okay, cassette tape are these things you had before CDs. And they have beginnings on it. They're wind them on school. You wind them on school, you listen to the tape, it gets back to the beginning, you go, well, what's before that? You go, what do you mean what's before that? That's the beginning. There isn't a before that. Time and space are properties of the universe itself. Therefore, you can't say what happens before, because there isn't a before, because there isn't time.
Time is, we know it
doesn't exist before, because there isn't a before. It doesn't make any sense. It's like asking what the water is. A bunch of fish are in a fish tank. I mean, what's the water like outside the tank? What? There isn't any water outside the tank. But because they're stuck in the water, they can't tell the difference. Sorry, this fellow's been waiting a while. Yes?
Just a question about earlier. You said when you're testing for the electron, it doesn't show up until you look for it.
Yep.
Does that mean it doesn't exist, or it is just not present?
It does not exist. The probability wave is there. I mean, if you interact with that probability wave with another probability wave, like let's say a photon of light, then they'll both go and pop into one place. But the electron as a thing wasn't sitting there before you went out and measured it.
Regardless whether or not somebody is observing or not?
The observing is the measuring. How else can you observe without measuring? That's what I'm saying. The observe is the measure. This is what's again these tricky questions. Go, wait, what counts as an observation? Think of it as being this way. Instead of using observation, I very much prefer to use the word interaction. Because I can think of, I go, oh, a photon hit it. That counts as an observation because it interacted with its wave function. That counts. And so imagine a universe where there's just an electron, one electron, and our little toy model. And it's just sitting there. It's a probability wave smeared out. And then I somehow shoot a photon in from outside the universe. And it goes, boom, and hits into the wave function. Then the electron will go and pop into place right there. It didn't exist in any one specific spatially localized thing before that moment. And that's the thing that's provable with Bell's inequality. Because before that, everybody said, well, maybe the electron's just sitting there and we don't know it. And Bell's inequality gave a fundamentally testable way to see if the electron's really sitting there or whether or not it's some smeared out wave, and then when you measure it, it goes bang and pops into one place.
Would you be able to claim that the electron would be moving along the probability curve? And
that would be the Bohm pilot wave interpretation.
And then when you had an interaction with a snapshot, that's just where it happened.
Where it happened to pop up.
When that happened.
Absolutely. And that's what David Bohm said. That was the pilot wave interpretation. There's a wave that's guiding where the electron's moving. The electron's really there, but it just looks like it's a probability thing because you can't tell until you interact with it. And the problem is Bohm's interpretation is still consistent with Bell's inequality. So it is possible that the electron really is there, and flying around like on a track like a roller coaster through space. And we can't see the pilot wave, but you can see the electron moving around. And so you go, oh, I can see that. That's fine. The reason some people don't prefer that is because it requires the postulation of an existing thing, an additional thing, which you cannot measure, the pilot wave itself. The universe is expanding. There's bad news. It's speeding up. It's okay. It's going to rip itself apart, but not for like billions of years. You're fine. In 1998, it was shown that the universe is not only expanding, but speeding up. Instead, we knew the universe came from some big bang, and it was thought prior to 98 that the universe was doing this, and all the matter in the universe was slowing it down. So if there was enough matter in the universe would go, look like a balloon, stop, bam, you go into a big crunch. If there wasn't enough matter to seal it back up, the universe would go, and it would just keep expanding forever, maybe slower and slower and slower. Okay. The problem is, in 1998, they showed using supernovae that not only is the universe expanding, but it's speeding up while it's doing it. It's like you took a balloon and went faster and faster and faster. You're going, well, wait a minute, how is that happening? Now, in physics, to produce a force, you have to have a change in energy. The change in energy with respect to space is what gives you a force in the first place. And for any of you who've taken physics, Newton's second law says to produce an acceleration, you have to have a force. So therefore, people start going, well, the universe is accelerating, therefore there must be a force. In order to be a force, there must be a change in energy. I don't know what it is. I think I'll name it dark energy because that sounds cool. And so nobody knows. At least not that I know. I'm sure there are cosmologists who are more knowledgeable, far more knowledgeable than I. But I know that whoever figures out the nature of dark energy will win the Nobel Prize. There's no question in my mind. Because no one can figure out why the universe is accelerating.
If the Big Bang is the origin of our universe, and there's no other forces acting on it, then couldn't you just argue that the Big Bang happened and that's why it's expanding?
It would, but would it account for why it's speeding up? The expansion is okay. You're allowed to have a boom and get bigger. The Big Bang is giving you this original kickoff to make the space go bigger. But it doesn't make it go whoop and keep speeding up even now. That's the part we're stuck with. As far as I know, the universe will eventually undergo what's called the Big Rip. So that's the latest I've seen out there, but I'm not positive. Meaning the universe will get so far apart, all points in space-time will get so far apart, that you will rip space-time itself. The fabric of the universe will tear.
So, how do we make our devices and measuring tools more precise? Like, if we had a quantum computing computer, does it take a lot of energy to be sustained and functional? And is it worth spending money on, or is it dangerous? Like you mentioned, recreating the Big Bang. What if that goes wrong?
Okay. First of all, these are the kind of questions that any good scientific endeavor has to ask. One, how are you going to get better measurements? What's the smallest measuring device you can possibly generate? And you could think of things like maybe single atoms. If I made a detector out of one atom and something interacted with that one atom, I could make something happen. You go, well, I could have as small as that? Maybe. What about one electron? I somehow hold an electron in place, and then when a wave hits it, the electron changes. And that changes a voltage in some circuit. Maybe I could use that to make a microcircuit. Something like that might work. Right. I was at the conference on quantum computation, and I asked one of the biggest people who are, David Presco is one of the world's best experts at quantum information theory to this day. And I asked, John Presco, not David, sorry. And I asked John, thank you ladies for coming. It's been a real pleasure having you. Thank you so much. I asked him, is it possible that you could do computation instead of being with individual electrons and protons? Could you do them on the quarks that were making up the protons, thereby giving you a computer that was even smaller, that used the states of a quark? This is a whole field called quantum chromodynamics. It's even smaller than quantum mechanics. And he said maybe. It's never been done before, and no one's ever developed a theory of it, but it's not excluded. And so you go, well, maybe using our current knowledge base, that's the smallest computer or smallest detector you could ever build as a quark. Right? Any smaller than that, you're at the level of these strings, which we can't even detect yet. So if they're down there, maybe in 1,000 years, you can imagine some detector that runs on string theory, but you'd have to figure out the string theory first to test it. So we're still way away from that. So the smallest thing we actually know exists, that you go, I could interact with that if I did something right, is a quark that exists in things like protons. Now, you were asking me, is it worth the money? I have no idea. I often tell people this. A lot of people, a lot of my students will say things like in my physical science or whatever, my astronomy class. They'll go, is it worth it to spend money on research on stuff? One, I think so, because it's just cool to know stuff. It's just cool to find things out. But I can do one better than that, because you go, hey, we could use that money for helping other people or something. Why are we spending it on research? If you had come around in the 1890s when they first discovered the electron and say, hey, look, I found this thing called an electron. And this guy named Maxwell, like 10 years ago, figured out this thing called electricity and magnetism. And we can do all kinds of neat stuff with electrons, like move them along metal now, like make wires. People go, who cares? I have my wood-burning stove. I have my mule that pulls the plow. I have my horse to ride. What else do I need? Today, look at this place. Everything. We go nuts if the lights shut off. Because without the discovery, you can't make the technology. I'll give you one more really easy one that's one of the clearest ones, and you guys will use this a lot because you're all internet people. One-way functions were discovered in the 1850s. These are functions that are harder to do one way than another. For example, what's the opposite of addition? Guys, it's not a trick question, it's really easy. What's the opposite of multiplication? Division. So those are two-way functions. It's just as easy to add something. If I go add 5, and get it back to the original number, you'll just go subtract 5. Right? If I go multiply something by 3, get it back to the original number, you divide by 3. Done. That piece of cake. Some functions are one way, meaning they're harder to do one way than another. For example, give me 2 prime numbers. Anyone? 7 and 3 makes 21. Right? I multiply 2 primes. Now work backwards and give me the original prime numbers. I go, here's 21. Tell me what the prime numbers are. Now, it's a small number, right? So you could sit there and go, oh, it's 3 and 7. No problem. But what if that number were really, really big, like 20 digits long? How would you find the prime factors that you use to multiply to make it? How would you do it? You have to expand it. Do you ever remember factor trees from school? You'd have to take it and go, okay, this is 2 times 3 times 5 times 7. Remember that? Remember what pain in the ass it was to sit there and go, give me all the factors of this number. It is much easier to multiply the numbers together than to take the big number and find its prime factors. That is a one-way function. It's easier to do it than to go backwards again. And so the point is, you're going, well, who cares? They figured this out in the 1850s and 60s. Anybody know what it's used for today? One giant technology, you use it all the time. Yes, sir? Encryption. Encryption. The public key encryption system that powers the internet is run off of the idea that I can give you a public key, which is a really big prime number, and I'm holding the other really big prime number called a private key. And so with it, you can use that public key to encode everything and buy stuff on the internet. Without it, you would have no secure internet transactions. We would have to take the 20 or 30 years that it took them to figure out that those things work and do it all over again. We'd have to start today and do it all over again. Think of how many billions of dollars would be lost in e-commerce. Entire ways economies are built today of buying things with PayPal, eBay, Amazon, Netflix. Everything you buy on the internet, you couldn't do it because there would be no secure way to transmit credit card information without one-way functions. And if you'd asked somebody in 1860, hey, what is this good for? What do you think they'd say? Nothing. It's like anything. I don't know. We haven't invented electricity yet, let alone a computer, let alone an internet, let alone eBay. And so there's no use for it. And so regularly research is used for something later on that we couldn't have known about at the time it was invented. Yes, sir, in the back.
Certain very simple systems have been solved quantum mechanically. We can model them exactly like the hydrogen atom.
Yep.
But then when we get to more complex systems, we lose the ability to get to the solution. So can you describe why that is and sort of where we've gotten to?
Yeah. The equation that governs where, what we're solving for, the bottom line, which is 1 at the bottom, is where the particle will be at some given time, right? The probability wave. Once you have that, you can extract other quantities. We call them observables, like the energy of the particle, the spin of the particle, the charge, the angular momentum, these things that describe what the particle, they're like little identification tags on the particle. And the problem is that the equation that describes this is what's called the Schrodinger equation. It's this big, long monster equation in quantum mechanics. And so solving it as in a branch of calculus called differential equations, you can go backwards and try to solve this thing. Well, the problem is the more individual pieces you put in, like the more electrons, the more protons, the more neutrons, the longer the equation gets. And the terms become so convoluted that there isn't a way, and this is going to sound kind of weird, there isn't a way to generate what's called an analytic solution, meaning an exact answer, like x equals this. So instead, you use a computer. You just grind it into a computer and say, I plug in this, what do I get out? And it'll give you a number. You give them another number, it gives you another number. And so you plot it out with a computer. It's kind of like the ability, if you take an algebra, you can all draw a graph of y equals x. Right? It's just a straight line going up. Imagine if you didn't have the equation y equals x. Can you still plot a graph of y equals x? Like just with dots. If somebody said, give me this dot, and put a bunch of dots on the board, you could make the dots. You wouldn't have the equation that describes the line, but you would still have the line. Think about this very carefully. Go back and forth between the geometry of show me a line and the equation of y equals x. Right? When I say it doesn't have an analytic solution, it means there's no way to work your way through these mathematical grindings to get to an equation. You can still draw a graph, but you can't get the equation out of it. And so you get an approximate graph and then try to get close with it. And so to do that, we put it into a computer. The computer just runs it over and over and over and over and over again. Does that make sense? Yeah. If any of you are like super math people, these are what are called closed form solutions. There are no closed form solutions for certain types of non-analytic problems. If you're in calculus, this is stuff you get to just past the ordinary differential equations course. Yes?
What kind of careers are produced from studying quantum mechanics? Like, do they need statisticians or engineers?
Good question. Mathematicians, yeah, the people that would normally come into this kind of field would be what we call high energy physicists. Sometimes what's called a condensed matter theorist, a mathematician. If you really want to apply this kind of stuff, you're going, okay, I want to use the heavy duty mathematics on the coolest front edge of research today. I can tell you right now, things like bioinformatics is a super hot area and will be. Like right now, if you had to go get a degree in something and go, hey, I want to make sure I can still get a job, something like bioinformatics will still use things like the statistical mechanics or the computational models and apply them to biological things like proteins, enzymes, chemical reactions. I have a friend right now who works in metabolomics, where they pretty much take a cell that's diseased with cancer and throw it on the wall and run it through a grinder and spit it on the wall. And based upon how the spit pattern comes out on the wall, they can tell you what was inside the cell. And so they need massive computer power to sit there and go, you know how many different possible, there are like 5 million different species of bacteria in your stomach right now. Can you imagine taking every single one of them and cataloging them all and going, okay, look at this, like a fingerprint, and work backwards? The statistical analysis on that is huge. Metabolomics over at UCSD, it's one of the hottest areas right now because they can work backwards and just go, give me your diseased cell, I'll tell you what's wrong with you. They're very simple. And so that's massive computer science. If you want the most versatile degree, if you're saying I want a career option that's very versatile, I would say if I were in your field right now, I'd go get a degree in computer science with a minor in either math, like emphasizing statistics, or biology. Something like that. Or maybe neuroscience. Because in terms of endeavors, and this is one of the things people don't like, it's hard to see it until you really think about the big picture. Think about it this way. What was chemistry before it had numbers on it? What do we call it when we were trying to just turn lead into gold? Alchemy. Alchemy. Right? We just kind of, I don't know, throw this or that and see what happens. And then we started going, hey, look, when I do this, it always comes out in these certain proportions. Let's make a new field. We'll call it chemistry. Right? Physics started out as a field called natural philosophy. And then once we started putting numbers on it, it became more quantified. It was more rigorous. We could make better predictions. Because when you put numbers on it, I can predict what the number will be at the next moment. Right? Think about the same thing now that we are just now in your lifetime developing the tools to do this with things like biology and cognitive science or neuroscience, depending on which area you're in. Before this, everything even up until 20 years ago was taxonomical, meaning I would tell you parts of things and pieces of things, but I couldn't use mathematical equations to describe things very easily. I couldn't use equations to describe neural firing patterns in the brain or how proteins will fold using statistics. That's only been within the last 20 years that we've had the math and the computers to do it. And so this is a whole new field that's opened up for you guys. Within 20 years, you're going to create every single disease using customized virus vectors that we can build from the ground up because somebody like you is going to go, hey, here's how I do it. Put it into your little super quantum computer, and then you go, okay, throw this much phosphorus, this much hydrogen, nitrogen, carbon, and oxygen, and put them in this, and shake them on a plate just like that. And a virus will pop out. And that virus will be used to carry a cure. We will engineer biology because we're just now getting to the point that we can put numbers onto it. And so that's wide open as a field. Well, I think that we'll have supercomputers or quantum computers because we'll put them in areas where it's really hard to get energy into the system. It'd be isolated. Putting them on a tablet's kind of hard to do. But you could imagine a tablet with an app that goes over the internet and then puts the problem into the quantum computer for you.
Oh, okay.
And then now it's running and just spits the answer back to your tablet. We don't need the computer on your pad anymore. We just need to have a communication channel. Yes, sir.
I saw this show, it was Vice, and oncologists are reprogramming HIV to attack leukemia, and also the head colds for certain brain tumors, like the common cold virus.
Sure.
So it's pretty crazy that this is already happening.
Well, there was one, I don't know if it was Vice, I saw this like a year or two ago, and it's the quintessential, it's the one that you like to see, right? I saw this, there's this nice little old lady, and she's baking cookies. And I can't remember her name, I'll call her Gladys. You know, Gladys is baking cookies. 5 years ago, Gladys was diagnosed with a type of brain cancer that has a 100% mortality rate within 1 year. And I'm going, they must have made a mistake, because they just said it was 5 years ago that she was diagnosed. I'm like, these producers suck. It turns out that Gladys is in a trial at Duke University, and this might be the one you're talking about, where they reprogram the virus to attack brain cancer. But yeah, this is in like phase 3 trials at Duke, where they've got like hundreds of people now that have just this type of brain cancer that's completely inoperable because you can't cut their head open while they have their heads working. And so you go, well, I'm kind of stuck. And so now this virus just goes, hey, let me get in the bloodstream, head up to the brain, and I'll only attack cancer cells. Done. No more brain cancer. Have a good day. I know it sounds crazy, but I truly believe that some of you that are like, just college age now, might not ever die. If you don't believe me, look at Time Magazine last month. They had an article that was talking about how kids that are born today could live to be like 180. Imagine, if you wiped out all the causes of why cells die, why would you ever die? Barring that you get hit by a bus. Oh, I'm going to get hit by a bus!
Barring murder events.
Yeah, besides the usual problems. If there's no reason for anything like heart disease or cancer to hurt you anymore, then what's the problem? Stop your cells from aging by stopping the telomeres from being broken off at the end of your genetic sequences. Your cells don't die anymore. They're done.
They stop aging too.
They would stop aging entirely. There are two major causes of cell death. There are telomeres, meaning these little bits of genetic sequences on the end of your genes inside each cell. And every time your cell divides, they go click and they break off a little slice. Every time it divides again, it's click, breaks off a slice. It's like a built-in clock. And so every time you break off a little bit of it, and when it's divided enough times, your cell will quit dividing. This is how you keep from getting more cells. This is how you keep from replenishing cells for everyone. Why do babies keep getting more cells, but past some certain age it doesn't happen anymore? That's why. And so they already know the enzyme that does this is called telomerase. And the idea is it possible you create a telomerase inhibitor that would stop that enzyme from breaking off the piece? Why not? Why is that so crazy? It sounds nuts until you think about the fact that 100 years ago we already knew that germs cause diseases yet. Imagine, nobody knew. Like, oh, you just died. You didn't know it was because of a bacteria. Today you get an antibiotic, you're fine. Is it possible a virus can mutate and have unintended consequences? Of course. Doesn't that happen, though, in nature all the time already? Every year it happens. Right? We just get better at it, and we make sure that the good outweighs the bad. Is it possible that we're going to engineer some pretty bad stuff? Absolutely. I'm honest, because you guys, probably know you were at my last talk on brain-computer interfaces, and the idea that you can, use EEG data to actually tell whether or not a person's lying. I know a guy right now does it with an 80% accuracy, and you can't fool him. I know a guy right now at the University of Graz in Berlin that does it right now. Things like this, you go, is this ethical, and what's it going to lead to? These are important questions. The thing that I don't like about these systems is that persons are smart. We are all smart. We could sit here right now and go, do you think this is a good idea? And we'll talk about the balances. But what's that expression from Men in Black? Persons are smart, people are dumb. You put enough people in a group, and somebody will do the bad thing. Somebody is going to do the wrong thing. There's always one bad apple. And so the point is, my personal thinking is that we develop the technology responsibly, because if we don't, somebody will and do it poorly. They'll do it the wrong way. They'll use it for bad things. And so if we're trying to be responsible with it, we can do better. In the long run, the system adjusts itself. The problem is it takes a long time, and people will inevitably get hurt. Every expansion, nuclear tests have killed people in the past. Hiroshima, Nagasaki. Of course, we have a world that now has nuclear weapons in it, but we also have nuclear power. We also have proton beam therapy right up at Loma Linda Hospital. One of only like 4 places in the world where they throw protons to kill tumors, one atom at a time, or one molecule at a time. That was absolutely impossible. You just died from it, even 20 years ago.
Well, the antibiotics that are not working anymore.
Say the antibiotics. Now we have antibiotic-resistant superbugs, right? And so the problem is, this is always a race to try to stay ahead of the bad things we produce. And the only question is, do we produce more good than harm? Think about this very carefully. That's the one real question you have to ask yourself. do you believe that the technology that we develop, whether it be quantum computers or EEG technology for brain-computer interfaces, can we use it to do more good than harm? I hope so. But maybe, it could be Pollyanna, man, I don't know, sure, we're all great people. That could be totally wrong. I have no clue. I can just tell you that we've had nuclear weapons since the 1940s and we're all still here. Yeah.
I read an article a couple of months ago that they created solid light.
That's kind of misleading. It makes it sound really confusing. How can you make the light a solid?
Right.
What they did was stop the light, meaning they got it to move almost at a zero speed. And even when you say it stopped, it isn't really stopped. The reason this is confusing is because people hear the speed of light as a constant. It's just some number that you're stuck at, right? But the problem is when light moves through any material, like let's say light's moving through that glass in the back of the window, it has to interact with the glass atoms. They'll be like, there's a glass atom, it goes, boom, the glass atom absorbs it and shakes for a moment, and then re-emits the light. Does that make sense? It has to interact, it hits it, it absorbs it, makes the atom shake with some more kinetic energy, and then the atom re-emits the light, and it goes, boom, and it goes through. But the window is like several layers thick, right, of atoms. It's like this big, giant wall of barriers in the way. So what happens is the light goes, an atom gets absorbed, gets re-emitted, goes to the next layer of atoms, gets absorbed, gets re-emitted, hits the next layer, gets absorbed, re-emitted. This is like somebody trying to run through a crowd, right? You're going, the person can run at 15 miles an hour. The problem is they keep bumping into everybody along the way and it slows them down, right? And so what you're seeing when you go, the speed of light is, and you'll go, it's like whatever, 1 meter per second, some really small number. What they've done is create a super, super, super dense material. It's like shoving a bunch of people in a crowd together, and the light has to go bang, 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 and hit through every single person on the way before you get out the other side. And that's why you're seeing that effect. MIT has a video of it. They slowed light down, but it's not even a meter a second, it's slower than that. It's like on the order of centimeters a second. And you can see it'll be going through like this big long tube. It looks like glass, but it's still like this fluid that's super dense. And you'll see the light go like in slow motion as it hits in little bits, like pieces will refract at you. You look it up, it's on YouTube. MIT has a video of them doing it. Yeah, David.
Is light doing something similar within the core of the sun before it even comes out?
Absolutely. Light has to interact with the particles on the way out. This is why, how many people have taken astronomy here? Okay. Do you remember that when you see a supernova, you see the neutrinos first before the actual light from the supernova shows up? Because the light has to interact with all the crap on the way out. The neutrinos don't interact, they have very weakly interactive, so they just fly out and you can detect them. And that's why the light is slowed down by the junk in between.
So like a white dwarf star would never explode?
That's right. Well, what happens is it very slowly cools down because, and this is a little tricky, but anytime you have an accelerating particle that's charged, meaning like a proton or an electron, if it accelerates, meaning speeds up or slows down, or it changes direction, it gives off radiation, which is what we would see as light. It's called black body radiation. So this degenerate gas inside the white dwarf star is still going, the electrons are still shaking, and every little shake gives off a little bit of radiation. And as it does so, it slowly cools down. The problem is the cooling time is like billions and billions of years.
Right.
And so you never actually see it. But you actually would, if you watched it long enough, you see the white dwarf cool down, and it would become, are they calling them black dwarfs or brown dwarfs?
Brown dwarfs.
Brown dwarfs, like it's totally cooled down, it's just carbon, which is left over after the white dwarf is finished. So this is a ball of carbon sitting out in space.
So it basically becomes a big ball of rock.
Yeah, like a big carbon rock that's super, super, super dense. If you fuse heavier and heavier elements, like let's say it's hydrogen, it's just two protons coming together, right? I'm simplifying the picture a little bit, but this is the idea. Helium would be 4 protons, 2 here, 2 here. Bam, you gotta throw them together. Well, the problem is you get these guys closer together, it takes more and more gravity to get these guys to stick to each other because there are 4 of them instead of just 2. Right? All the protons want to repel each other. So you get them close to the other and go, I'm out of here, and push apart. So the bigger the element, the more energy you have to have in it to get it to stick together in the first place. And so in the white dwarf, the mass of the thing has to be less than what we call 1.4 solar masses, meaning a solar mass is the amount of stuff in our sun. So 1.4 would be like 1.4 suns of our sun. If it's heavier than that, there's enough pressure to make those things collapse and become a neutron star. If not, it fuses up through carbon with all the gravitational pressure that it has. Then that can't go anymore. It doesn't have enough pressure to make the carbons fuse into something heavier. All right, guys, I really appreciate you coming. If you have more questions, we can stay all night if you want. I don't care. I just want to finish.